Welcome to the California Colloquium on Water. I'm David Sedlak, and Nari couldn't make it today, so I'm going to introduce our speaker. I guess our speaker needs no introduction. Nari said I had to give an introduction, so I'm going to give one. Jim, speaker today. Some of you know Professor Morgan is an emeritus professor from Caltech. He got his bachelor's degree at Manhattan College in 1954, and his master's degree from University of Michigan in 1956, and then a master's and a PhD from Harvard finally in 1964. And after a brief stay at University of Florida, I believe, it was off to Caltech, and he's been there ever since. People know Professor Morgan in several different ways. Some of you have struggled through Stuhm and Morgan, the textbook, which first came out in 1970 and then came out in two later versions or two later editions that are very popular and are really the definitive reference book or textbook for aquatic chemistry, and really have taught us all a lot about how to view the role of chemicals in the environment. You may also know him as the founding editor of the journal Environmental Science and Technology, which he's handed off to a few other editors since then, and they've all had to struggle to keep up with his level of quality. You may also know him from his scientific studies of coagulation and manganese chemistry, which he's well known for in the field. Really the studies that taught environmental engineers how to use chemistry to understand what was formerly a black box system that was understood only empirically. And I think Professor Morgan could give us a talk on any of those things, his career in academia, being the editor of a journal, and probably two talks on manganese and coagulation. And he wanted to give a talk on manganese oxidation and would have liked to have done that. But I said, this is the Colloquium on Water, and we have engineers and scientists here, but we also have people from the social sciences, and we also have people from the humanities and the law school. And we really have to talk about something broader here. And so after much hemming and hawing and much thinking, he's decided to put together a talk for us which is going to address the connection between water quality and water quantity. And with that, his title that he gave us is the Water Quality Matrix, a quantity to quality transition to the new century. And before he gives his talk, I wanted to mention two administrative details. One is there's clipboards. There are clipboards coming around for you to sign up on. If you're not on the email mailing list for the Colloquium series, please put your name and email address on there. And then I wanted to announce the last speaker of the semester. On May 13th, Bill Preston from Cal Poly San Luis Obispo will be giving a talk titled The Environmental History of Tulare Lake. But today we have Professor Morgan, so I'll turn over the podium to him. And thank you again for coming, Jim.
I think I've already lost the mic. You see, I'm from a technological institution. I didn't count on actually getting up out of a chair. Figure if I stall long enough on this, I won't have to give the talk. But I'm very pleased to visit Berkeley again. Over the years, I've given a few seminars and a few lectures. Never one that I found as daunting as this one. That was implicit in the remarks of David that the hemming and hawing was all on my part. It wasn't on David's part. Now, the compromise that I've decided is to give 5 talks. 2 on manganese, 2 on coagulation, and 1 on the title. Okay. I'd like to begin with a remark, 2 remarks actually. And these are, these are remarks that I like to get out of the way in case I never get to the end of the seminar, and remarks so you'll know where I'm heading before I have the danger of getting lost in the joys of PowerPoint presentation. First, water has not been only H2O since early in Earth's history. 2, water quantity and quality are inextricably connected. The water cycle is an engine for transporting H2O, dissolved gases, acids and bases, salts, organic compounds, nuclides, and all manner of particles, minerals and biota, suspended, colloidal, and sedimentary. The quantities in the water cycle are thus the masses of H2O, solutes, and particles. For example, if the California aqueduct transports about 1 million acre-feet of water each year, or about 3 million tons of H2O daily, it simultaneously transports 2,000 tons of dissolved solids daily, and lesser amounts of other solutes and particles. Lakes and reservoirs retain transported particles which form sedimentary deposits. Over time, the deposits may capture or release quantities of contaminants, for example, arsenic, thereby affecting the quality of impounded water. Next and last, flow of runoff in a watershed may release appreciable quantities of solutes and particles to rivers and lakes, thereby also affecting water quality. My second set of remarks has to do with water quality. The term water quality, with quotes around it, appears to be an ill-defined one in common use. Actual water properties, for example, pH, temperature, calcium concentration, oxygen concentration, trace element concentrations, synthetic organic compound concentrations, nuclides, etc., do not describe, quote, water quality, end quote. The quality of water must be defined with reference to a criterion or standard, i.e. water quality is judged to be good or poor relative to a basis. The basis for defining water quality is the value of the property required for a particular beneficial use or purpose or goal. For example, arsenic in drinking water, the standard level will soon be taken as 10 micrograms per liter. A water supply might have an actual incoming arsenic level of 20 micrograms per liter. The quality is then 20 minus 10, the difference between actual, or with reversal of sign, which we always love to do at Caltech, we could call it plus, minus, but the unit is 10, and that's the measure of water quality. It's the departure from what we want for the use or purpose or goal. For sets of properties which impact water beneficial uses, the water quality comprises the vector of A and S values, actual values and standard values. And the scales for water quality or any other environmental quality have the units of the particular property, for example, milligrams per liter, organisms per volume, etc. The representation of the set of water quality measures relevant to several uses, for example, drinking, recreational use, ecosystem protection, and so forth. When you compare these to one another, the natural result is an array of numbers. So, now, why did I go to this long result? Because I was asked by one of the leading water authorities in the world, Malene Falkenmark of the Royal Institute of Technology. She said, "What do you think water quality means, Dr. Morgan?" I don't think anybody knows what it means. So I came back and I thought about it and I said, yes, I do. And Jack McKee knew when he wrote water quality criteria 50 years ago. It's the comparison between what is and what's desired or what is needed for a particular use. And the reason an array is required is we can't really, in general, speak of the water quality of just one application, because in our world today, and in California certainly, uses are in competition with one another, and there are different requirements for those uses. Oh, hell.
No, oops. You said yes.
I hate these things. Now, isn't that a nice slide? Aren't you glad you came to this talk?
It's pure water.
You're way ahead of me, which is very often the case. So now I'm having a little trouble. Ah, put it on the chalice. The chalice from the palace has the vessel that is true. All right. I begin with an invocation. A drop of water fell in my hand, drawn from the Ganges and the Nile. On my index finger, the Caspian Sea isn't landlocked. There are not enough mouths to utter all your fleeting names, O water. The Nobel laureate for literature in 1996, from her book and poem View with a Grain of Sand. And now I give you my limited lexicon of all the words for water. Criticisms and amendments will be accepted in the discussion to follow this talk. This is where you are. This is what I purport to talk to you about. Notice the use of the Berkeley colors. 35 years of aquatic chemistry and water quality engineering are the credentials that I bring to you. This is my license plate. The origin is from James Joyce. The Reagan brow was to be seen ringsome on the aquaface. It's from Finnegan's Wake, the first page. And because I cite JAJ, James Aloysius Joyce himself, and because I want you to know that I'm an authentic water person, I'll tell you that in Pasadena, I paid $305 per acre foot of water. And so you're invited to make those comparisons too. A little bit about my general background. I came to Caltech in 1965. I want to mention just a few of the problems that I've worked on that are California water relevant. Sometimes I worked on them immediately and with my own hands. Other times through the intermediation of the state of California and its apparatus. The first problem I worked on was metal contaminants. Excuse me, now I have to go back, right? Metal contaminants in coastal sediments. The metal contaminants in the coastal sediments came from the sewage outfall of the county of Los Angeles. And we developed computer models and we used databases in order to see what the metal contaminants were, and we found out they were predominantly metal sulfides accumulating in the sediments. Later on, and not related to this talk, it was found that many other things, such as PCBs and DDT, were also accumulating in those same sediments. And with the wisdom of hindsight, the metal ions actually became useful tracers for the rate of accumulation of the sediments because they don't break down. And the sulfides tend to be buried and retained. The second problem I worked on was the river storm metal flows to the ocean. One of the hot questions in 1969-70 was, are all the metals that we see in Santa Monica Bay and off the coast of Orange County, are they all coming from sewage outfalls? And the answer was, if you know the answer, you can come in too. They also, the answer was no, that in the fall and winter storms, there are enormous quantities of all the trace metals being carried to the ocean, being washed out of the dry deposition before by the flow of rainfall. The third problem that I worked on with my student, Howard Liljestrand, was rainfall chemistry in the Los Angeles basin. Simultaneously with this, John McCall on the Berkeley faculty established a rainfall sampling network for the Bay Area. These were the first two sampling networks for the quality of rain in California. We had a network which covered essentially the Los Angeles basin. That led a few years later to the work of Michael Hoffman, my Caltech colleague, on acid fog in the valley, resulting largely from combustion in the Bakersfield area and opening up quite a rich area of science for aquatic chemistry, as Michael Hoffman liked to call it, up in the clouds. And lastly, in my role as advisor to the state of California, for 13 years I served as chairman of the Scientific Advisory Committee on Acid Deposition in the state of California, and that program was centered on acid deposition in the Sierras, the impact on the quality of Sierra lakes, and the impact on the quality of soils and and forest areas. That's just to show part of what I've been interested in. That's to show that I know how to break a presentation in part. Now, in the spirit of the times in which we live, and knowing that the title I gave in November might not mean in April what I had intended, I must deconstruct the title. So I'm deconstructing the title. To deconstruct the title, I consulted through intermediaries with Jacques Derrida, the famous deconstructionist. I only give his name as Jacques D because of the tenuous relationships between the United States and America at the present time. Terms, motifs, and character are defined by binary oppositions within a text. Oppositions are hierarchical, and these oppositions are unstable, reversible, and mutually dependent on one another. Whew. So I said, what does that mean? Or as David Byrne would say, how did I get here? Quantity and quality might seem to be in opposition under the rubric of Derrida's formulation, and translation might be taken to suggest a hierarchy of importance, one more important than the other. And the opposition will be found, in fact, to be unstable and to disclose dependence, as I've already argued, that they are inextricably intertwined. And what does matrix signify? Something that constitutes the place or point from which something else originates, the ground substance. Paracelsus in the 16th century. Water was the matrix of the world and all its creatures. Paracelsus also believed there were 4 elements. Well, nobody's perfect. In modern parlance, a rectangular array displaying linguistic features or other data. And derivative of mater, mother, from the Latin. One aspect of the water matrix is this illustration from Philip Ball's beautiful book on life's matrix, which illustrates inside a bacterial cell the water molecules, which are very, very small and are so small that they're not attempted to be shown. They're small in comparison with the proteins, the nucleic acids, the sugars, and amino acids, but as you know, they occupy 70 to 80% of the content of the cell. Well, this is a primal meaning of matrix, and it's only one of the meanings that I adduce in giving this title. And indeed, as you'll see, it's not the most important meaning for me in my presentation. Now, some of you have heard rumor that I'm partial, and in fact, I've already given evidence of it to James Joyce. That's 2 portraits of James J. by Brancusi. The one on the right you may recognize. The one on the left is a tad more abstract. One of my favorite quotations from Joyce, I'll give in part, is his reflections on water. And I want to give this in order to back up my earlier assertion that water hasn't been H2O since the early days of Earth history. And the question begins with, what in water did Bloom, water lover, drawer, water carrier admire? Its universality, its ludo-fulvious bed, fulvic acids, its capacity to dissolve and hold in solution all soluble substance, including millions of tons of the most precious metals, its alluvial deposits, its secrecy in springs, the simplicity of its composition, 2 constituent parts of hydrogen, 1 constituent part of oxygen, its properties for cleansing, quenching thirst and fire, nourishing vegetation, its metamorphoses as vapor, mist, cloud, rain, sleet, snow, hail, its solidity in glaciers, icebergs, and ice flows. Water is not just H2O, and it has a rich history, as I'll try to show or schematicize, both in the world of emotions and effects, as well as in the world of science. So, the left hand. Unfortunately, on my computer, I only have the same image for the left hand and the right hand. But I'll show you the right hand. The right hand is obviously blue. The left hand is obviously red. I want to show you examples of the left hand of water. Creation, sacredness, dreams, metaphor, myth, beauty, purity, values, and biophilia, to use the term that E.O. Wilson uses. And I might add at the bottom, hydrophilia, the love of water as an important overriding human emotion. And the right hand of water, what probably more of us think of, H2O, health, chemistry, biology, cycles, value, technology, ethics, law, and I'm afraid other things that come to mind that I haven't listed. A quote for the left-hand side from the 11th century, water, the blood of the universe, a Chinese quotation. And a quote from Malin Falkenmark, the aforementioned, from 10 years ago. In a world with rapidly growing population, water quality management should become as important as water quantity management is today. I want now to affirm my personal commitment and my lifelong association with Werner Stumm, who taught me this commitment. Aquatic chemistry and water quality engineering, the two things that have occupied myself and my students for most of my time at Caltech and before, that it is for the protection of aquatic ecosystems and human health. This is an argument made very forcefully by Peter Glick, who points out the dangers of tilting toward the human use of water as a consumable product and neglecting. And these two examples are a beautiful wilderness site with water and the water treatment plant of the Department of Water and Power of the City of Los Angeles, with the treatment plant in the foreground and one of the storage reservoirs in the background. That has been, in fact, my agenda for much of my time, to understand the natural environment and the changes that are worked on it by both human and natural processes. It is a common misunderstanding that we need to treat water, for example, because of human intervention in the water cycle. It's not true. Many of the problems that we treat water to solve are given to us by good old Madre herself in the form of natural phenomena. We might want to remove fluoride from water rather than add fluoride to water, for example, in certain parts of the United States and certain parts of the world. And now I'd like to give the quote that I hold very dear from Werner Stumm. The total quantity of fresh water on Earth could satisfy all needs if it were evenly distributed and accessible. We are concerned with the quality of the water and how it is affected by cultural developments. We think not only of immediate effects on the humans who drink the water, but also of the hazards imposed on water as a life support system, from an article called Water, an Endangered Ecosystem in 1986. All right. One of the things that I'd like to share with you is a certain historical perspective on the issue of quantity and quality from a fairly limited point of view. This is what I've come to know as Times River. Many of you who know me know that this is my metaphoric device for almost everything I want to talk about. So, quantity, capturing and transporting fresh water supply. New York's Croton System, 1890. Portland, Oregon's Aqueduct, 1895. Boston's Wachusett Aqueduct, 1908. New York's Catskill Aqueduct, 1915. Will he ever get to California? Yes, he will. Owens Valley, LA Aqueduct, 1913. San Francisco's Hetch Hetchy, 1923. East Bay Muds Macomely Aqueduct, 1930. The Colorado Aqueduct, 1941. The California Aqueduct, 1973. And on the boards now, not Californian, the Yangtze River aqueducts to the north, beginning in 2003 and expected to be finished in 50 years. Water will continue to be moved, but I think the issue that many societies face is that we are running out of places to go and get the water and bring it, other than the oceans and the icebergs, for example. So now I would use the same metaphoric device to talk about science and engineering and in the progression during the century just recently concluded. In the 19th century, the items in red are what I'll roughly call technological innovations which affected water quality engineering in major ways. Ozone in Europe before the turn of the century. Chlorination in the United States. Rapid sand filters in Canada and then in the United States, all in the first decade of this century. Activated sludge by Arden and Lockett in 1914, which I think aptly described by my colleague in the conversation this afternoon, David Sedlak, it is a river contained within a concrete box. And the environmental conditions are changed to optimize the breakdown of the things contained in the concrete box. And I think that's a very good way to think about many of our treatment processes. They are imitations and replications of nature. And dear to my heart, because it interested me in this field for the first time as an undergraduate at Manhattan College in 1952, the Streeter-Phelps equation, a model to predict the oxygen in a stream as a result of imposed domestic or industrial waste. In the middle part of the century, the pH meter was invented and commercialized by Arnold Beckman, 1933. Can you imagine what life was like before we had a pH meter? It was very difficult. Indicator papers were pretty much used, and it was rather an interesting challenge 30, 40 years later to go back and convert results inferred from acid-based litmus-type paper and convert them into a modern scale. Bayliss discovered the use of activated silica as a coagulant aid. Flocculator design by Thomas Camp was put on a scientific grounding in the 40s. And very dear to my heart, a scientific development here is Langmuir's index. Langmuir was a great applied chemist at Berkeley, and he developed the Langmuir index, and the applicability of the Langmuir index developed at Berkeley was a direct consequence of the availability of the pH meter, because what Langmuir expressed was the tendency to precipitate calcium carbonate in a water system. He expressed it as a difference between one pH, the actual pH, and a pH which corresponded to the saturation of the solid phase. So those are very interesting, because a commercial development, a pH meter, actually led to a scientific and engineering development. It's not always that the science leads to the technology, although Beckman was a brilliant scientist as well as a brilliant inventor. Moving on, groundwater recharge became very important in the 60s. Reverse osmosis, excuse the buzz, RO, when I forget to tell you, it's reverse osmosis. These are membranes that are used to separate out water from waters plus salts, or in other contexts, to separate water from particles. And that takes us to takes us into the area of the end of the century. Polymer flocculants. New chemicals became available and used experimentally in the 60s, 70s, and into the 80s, and they actually revolutionized many aspects of water treatment and wastewater treatment. Enhanced coagulation became very, very important in the 70s and into the 80s in order to remove some of the precursors of the disinfection byproducts that resulted from chlorination of surface waters containing natural organic compounds. Direct filtration. And then the wider use of ozone in the US. Now, I gave this talk in Ann Arbor, not this talk, but I mentioned this development of ozone in the US, and a man rose up in high dudgeon and said, "We used ozone in Monroe, Michigan in 1908. I said, "I'm so glad." But he said, "So I don't want you to think that it was discovered later. We did it." And so this is just a sort of signature of what's been going on in the last 10, 15 years. There's been a great interest in application in ozone because it protects waters in ways that chlorine, the earlier disinfectant of choice, cannot do. Advanced oxidation processes and photocatalysis to destroy pollutants are all recent developments. Over here, I want to point out microfiltration and ultrafiltration. Microfiltration is roughly what you would use to remove microorganisms, to capture them by their size and not go through the pore. Ultrafiltration will take out polymeric and larger molecules like proteins and so forth. And back at reverse osmosis, those were essentially molecular sieves, or things that would take out things the size of a few water molecules, hydrating anions, cations, and organic matter. One of the major contentious issues of the last 10 to 15 years has been to filter or not to filter. Many of the water supplies in the United States developed early through going great distances to capture the water, do not filter the water. They depend upon chlorination of the water or other methods of treatment to make the water safe and to protect humans from diseases spread by pathogens. I recommend a report to you published by the National Research Council about 2 years ago, 3 years ago, on a thorough examination of this particular question with respect to the water supply of the city of New York. And one of the consequences of that study will turn up again in my lecture when I mention the difference between a technological solution and a management solution. Basically, the management solution is an attempt to guarantee or protect the quality of the water on the watershed 150 miles from New York or so. The technological solution would be to chlorinate more, or even a proposal that was made in the 60s was to treat the Hudson River. That was a serious proposal by one of the leading water authorities of the time. And it was vigorously contested by one of the other leading authorities, Gordon Fair, whose remark was you should always go as far as necessary to get water of the best quality. And Abel Woolman said, Hudson River's right nearby. And well, we haven't started to use the Hudson River yet. Okay, a little list of things that I want you to be well, not aware of. I'm going to mention that these are hot issues, hot button issues, and maybe increasingly so. Arsenic in drinking water has gone through a very intense wave of research and new standard setting, new criteria and new standard setting. Cryptosporidium. What did I do?
Just hit your space bar. Yeah, something like that.
Thank you. Did it get... It lost interest or something of that sort? Okay. Okay. Cryptosporidium is one of the really tough problems because chlorine will not treat it, and that's one of the reasons for going to ozone, and it's also one of the arguments for filtration, that you can remove these particles. I'll later on give you a way of thinking about how big these things are. As an aside, let me tell you, especially the students, that if you're going to follow a career in science, and expect to attend many seminars, it's always important to have a penetrating question to ask the speaker at the end of the seminar. I give you 3 for your consideration. 1, what is the effective temperature on the process you've just told us about? 2, what is the effective pH on the process you've just told us about? 3, how big is the particle you've been talking about? And I'll return to that later. Chromium-6 in water, still a very important issue in Southern California. Methyl tert-butyl ether has gotten a lot of attention. One of those compounds that was used for a very laudable purpose to control air pollution and had a secondary effect of contaminating groundwater supplies. Perchlorate in aquifers. When I was a graduate student at Harvard, I threw away perchlorate salts by the liter down the drain in Cambridge. But about 5 years or so ago, perchlorate became discovered as a very important contaminant in groundwaters, and the source was the disposal of materials that were used in rocket propellant processing. And around the Los Angeles area, and probably in other areas that I'm not familiar with, there is serious concern about how to remove perchlorate, which is a potential carcinogen. And last, down at the bottom, pharmaceuticals and streams, which is a very intensely studied area here at Berkeley in the laboratory of David Sedlak. Okay, the aforementioned how big is it question. I like to think of a size spectrum of particles when I'm thinking of treatment processes and natural processes. So let me begin at the big end. Suspended particles, bacteria, algae, protozoa going up, and viruses much smaller, and particles in the domain called colloidal, which for the most part means smaller than about 10 to the minus 4 centimeters or 1 micrometer, down to molecules. And these are some of the laboratory systems that I know have been studied: iron oxide, silicon dioxide, calcium carbonate. And these are the microfilters. This is the size, sort of the rough size cutoff. See, you'd capture bacteria. The ultrafilters, see, you could capture a fair amount of the colloidal particles. And then the nanofilters, which actually remove molecules. Now, this is what I call sort of a modest particle size distribution. a sort of bare bones particle size distribution. But there's more. There's the aquatic scientist's particle distribution, which I first presented in a very, very modest form, drawn on the back of a piece of plastic 6 years ago, to the enormous irritation of David Jenkins, a member of this faculty. Now, this is a way of orienting yourself in what I call particle size space and concentration space. And I won't exhaust all the possibilities, but I want to tell you that down here we're talking about molecules, salts in seawater, oxygen, hydrogen ions in water. Here is one of the most important basal water quality properties for water supplies and all natural waters, aquatic natural organic matter, used sometimes called DOC, natural organic matter. And what you want to know about it when you read reports in this area is that, in fact, it's not just one size. It has a distribution of molecular sizes depending on where it comes from, how it's been processed. And then suspended solids, the things that are captured by filters, for example, or removed in settling basins, or in rivers, or in reservoirs, have also particle size distributions. It's important to know where the viruses are and why it's difficult to remove them. They're much smaller than the bacteria. Here are the sizes of the Cryptosporidium cysts. Here's the sizes of the coliforms in here. And here, which is, I must admit, very speculative, is the estimated concentration and particle size of the Loch Ness Monster. Mike Cavanaugh thinks that I've misinterpreted the concentration of the Loch Ness Monster, but it's a singular value anyway, and there's no point in arguing a lot about it. Okay. Now I want to go through a series of exemplifications of the environmental engineering cum environmental science aspect of the water quality issue. I want to show the various parts that are required in order to come to a proper understanding of environmental quality and the implication, the development of environmental policy and standards. Sciences very often interpreted with environmental models, which can be of great complexity, and this is a highly developed art form in environmental engineering in the last 25 years. In fact, we depend very, very much in many areas of applied science on models that have been vetted and that can be used to make predictions even of such things as fisheries, all sorts of things. So environmental engineering analysis, that doesn't mean, just to be clear about my lingo, doesn't mean water analysis. It means an engineering analysis of the problem to be solved. When people develop buildings, you do an analysis of the requirements of the building, and then you do a design. Well, in environmental systems, it is the same way. We have to have a proper analysis of the treatment process, the behavior in the groundwater, developed through models and so forth, and that leads essentially to an environmental engineering design. Very important are the establishment of environmental quality criteria, in this case for water. There are 83 regulated substances, at least at the present time, and there are about 40 more substances that are called secondary or of scientific interest in relation to them. That feeds into environmental engineering design because when we know actual water composition and know water quality criteria, we know what we have to do in principle. Environmental technology, new processes, for example, the use of polymers, the use of new methods of filtration, the creation of membranes with ability to remove molecules or particles or larger particles. I call this technology to distinguish it from another important part, which is environmental engineering design, which requires the putting together of technological information with analysis in order to design systems to solve problems. Another very important part, which occupies a very, very large part of the national budget and the state budget in the area of air quality, water quality, and a variety of other quality issues, is in the field of environmental measurements. This is an area in which progress needs to be made and continues to be made to measure things more specifically, that is, to find out actual compounds that may not have been identified and quantified before, but also to go, when necessary, to lower levels of detection in order to find out if things that we are concerned about by forecasting are actually present in some of our systems. Environmental measurements are very often related to new technology, as in the classical example of the pH meter of Arnold Beckman. But we have the ability to do environmental work in water increasingly better because of the technology of measurement, which then manifests itself in more accurate and more reliable measurements. And then environmental policy, the consequence of all this. And I want to show a linkage. Environmental policy is dependent upon what we know about environmental engineering design. We usually formulate policies to do what is possible. We very often cannot do things, and therefore we can't formulate policies to solve problems until the design or the technology has been developed. Sciences are probably the most important feed into the development of environmental quality criteria. For example, how do we know what the arsenic level should be? How do we know what the chromium level should be? How do we know what the pesticide X should be? That comes from science, some exposure models, and environmental quality criteria. Sciences also feed independently to environmental policy, a phenomenon of the last 30 years in all aspects of the environment, including water, as the interest in other science, of geneticists and molecular biologists and toxicologists who have become interested in applying their science to the issue of environmental policy. And that has created new challenges for engineers and applied scientists to answer some of the questions that are raised by new sciences applied to older problems. Sometimes it makes the traditional practitioners very unhappy because questions have to be answered, or at least have to be attempted to be answered, that haven't been thought of before because the problem is being addressed by people from a different scientific perspective. Now, I'd like to go through one example which is personal to me and will always be important, continues to be important in fresh waters, estuarine waters, of the United States and other countries developing along the lines that we have developed along in the United States. It'll look familiar, but it will be different in some detail. Sciences, I want to mention some of them just in passing. Microbiology and biochemistry are looming much larger in environmental work with respect to water today than at any time in the past. Environmental models, for example, for the Streeter-Phelps equation, and another form that's very, very important but not involved here is groundwater models. But for the Streeter-Phelps equation, the mathematical model which was developed 80 years ago is still the key for understanding what happens to a river or an estuary when waste loads are discharged. And the modern models require that you understand photosynthesis as well as deoxygenation through microbial decomposition. In other words, it becomes more elaborate with time. Environmental engineering analysis, sources of pollution. A very large part of what environmental engineers are required to do is to identify sources of pollution, to work out the hydrology of the surface water, the hydraulics, and to understand the implications of potential climate change, among other things, and to do research at the pilot scale in order to test out ideas. And then environmental engineering design. We have to design, those of us who do engineering work, processes and capacities. How big must the treatment plant be? What must the nature of the treatment plant be to solve the oxygen resource problem? That involves, again, looking at possible new technologies, high-rate biological processes, phosphorus and nitrogen removal, which was not a problem thought of when I was an undergraduate student and didn't become an important problem, that is nitrogen and phosphorus in relation to oxygen resources, until the mid-60s. We don't know at any given point in our trajectory my belief is that we don't know everything we need to know, and we have to continue to learn both the science and the technology as well as the policy implications. The environmental technology shows here feeding directly into environmental design. Okay, now the next to the concluding part of my talk. What quantity of water of a particular quality is needed for a given goal? This is a reformulation of a very valuable treatment of the subject by Peter Glick in his book, The World's Water, 2002 to 2003. One of the most valuable books if you're interested in having rich sources of data and also well thought out, argued positions about water policy. That is the question. This is one of my matrices. I told you there'd be matrices. The purpose of the water use, the property. Drinking, and this is not an exhaustive list, drinking, agriculture, manufacture, groundwater recharge, and ecosystem protection. What properties? Again, an illustrative list: arsenic, chromium, copper, coliforms, virus, cryptosporidium, turbidity, pH, and oxygen. And the list, as you know, will run to about 100 in the most general case. And much is already known about this. It's not that you have to discover this every time. But you do know that if you followed water protection quality, drinking water protection quality in the United States, that the list will grow longer. It must grow longer. It's dictated by law to grow longer. The job of the EPA is, in fact, to make the list longer on the basis of careful thinking and examination. Okay. Does it begin to look like a matrix, Arthur? It's suggestive. These are the standards, and they're double indexed. S1 means arsenic, and D means for drinking water. So you begin to formulate a matrix which shows you the property and the purpose for which the water is to be used and the property of that water. And then over here, just as a spare example, ecosystem protection, I will mention copper for toxicity to fish and phytoplankton. I'll mention pH for, in some cases, lakes. And I'll mention oxygen because that's always a central issue in rivers and lakes and estuaries. Now, to use an abbreviation for Peter Glick's notation, I'll call quantity just large Q for the goal. I use goal, by the way, because Peter Glick does not like the word use. And so I don't want to argue about a noun. I'll say use, purpose, goal. That's fine with me. I think that there is a tendency to worry, maybe with some reason, about use as if water was a commodity which was quote unquote used, but not necessarily valued. And so I'm quite flexible about having dialogue on that subject. The property in relation to the goal. Now, where contention will occur in many societies, our own and others, is that the sum of those goals, quantities for water, must total the withdrawals. For example, the water that you do not send south to Southern California for the Bay Delta is serving another valuable use in the Bay Delta system. And it is determining, in the long run, the amount of growth and water use in Southern California, appropriately so, because of conservation rules about supplies of water, which are not constant year after year, but which are statistically variable. All right, and then the last piece of the puzzle. I want to say that the engineering problem, the analysis problem, the policy problem in the New York system, in the Delta system, in the Colorado River system is this, that the actual property, say the arsenic, plus the management of that property goal must give the property goal. And by management, I will now amplify it This is actual means the source quality, what's in the source water. By management, I mean in Peter Glick's terms, hard or soft options, traditional technology or innovative methods of management and changing the behavior of consumers, persuasive approaches. It means many things, but at least it means those things. In the context of New York, it means changing the behavior of the people who occupy the watershed 150 miles from New York, so as to reduce the impact on the quality of the water by the time it reaches New York. New York has a lot at stake in having that happen because the alternative is filtration after the review of the policy. The property of the goal, the standard of quality needed. So why do I say management rather than treatment? Because of the lesson I learned in reading Peter Glick and reading Charlie O'Melia's NRC report on the Catskill project, because you don't necessarily have to solve every problem with another technological intervention. You need a judicious combination of a technological intervention, if available, and changing of water consumption practices. Is it true that I've heard that in the city of Sacramento, water is not metered? Well, if that's true, that's an interesting result of human behavior that could be changed. It's interesting that it's also the capital of this great state. So there are a variety of things which I need not draw out for you, which embrace both technological innovation, application of traditional technology, and encouragement of incentives for changing human behavior in relationship to the goals of using water. Now I want to spend a little bit exemplifying this concept on a very, to me, valuable paper published very recently by Tak Asano. It's a conceptual profile of water quality changes in municipal water treatment, water uses, wastewater treatment, and treatment for multiple uses. It's indeed possible that people in this audience have heard that expounded upon by Professor Asano earlier in this year or a previous year. Now, what I like about this figure is that it satisfies all the requirements of the ideal Caltech slide. The ideal Caltech slide makes no commitment to the numerical value of the x-axis or the y-axis. On the other hand, it is clearly a vector because the arrow points up. And time is certainly increasing to the right because the arrow points that way. This is the unpolluted source water, maybe of Tak implies different quality undefined. But you can understand what he means by it without any great exertion. The drinking water then is of improved quality. Then it is subject to municipal and industrial use. It is degraded in quality and becomes of the quality of wastewater. Then wastewater treatment at different levels improves the quality, and then water reclamation and reuse through a variety of processes improves it still further so that the water can be reclaimed and repurified. What are some of the processes used? I think different people are familiar with different aspects. For example, advanced oxidation, absorption on activated carbon, membrane filtration, reverse osmosis, UV disinfection, coagulation, etc., etc. Categories of reuse suggested by Asano: agricultural irrigation, landscape irrigation, which is clearly different, has different quality requirements. Landscape versus agricultural, industrial water, groundwater recharge, non-potable urban use, and the ultimate big question being addressed by many societies in different parts of the world: direct potable reuse, that is, the direct reuse of a highly treated former waste for drinking water, potable, drinkable. So I repeat again, what the quality of the water then means the algebraic sum properly constructed between the actual property and the property of the goal in whatever the use is. So that's what this scale means. This scale can be given in great detail. It's not just a single numeric scale. it is in fact an array of results which correspond to uses and properties. The example I give down here is the one I've already given before, which is arsenic, the difference between 10 and 20 being a measure of the water quality. Now I want to give 3 brief examples of research that provides part of the underpinning of what I've been saying about the issues of improving understanding water quality. The first example is from the work of Janet Herring, my Caltech colleague, in the water supply source of the city of Los Angeles, which is up in the area of Owens Valley near Mono Lake. The water that is the source coming from hot springs, one of the feeder springs, is in fact contains arsenic in the 3 oxidation state, the more worrisome form of arsenic. And when arsenic becomes arsenic 5, it becomes less harmful, although perhaps more easily transported. The purpose of this work is to show that as the distance goes downstream of the gorge that feeds the river that eventually becomes the Los Angeles aqueduct, the arsenic total changes very, very little, but the arsenic 3 disappears. The arsenic 3 is in fact being converted from arsenic 3 to arsenic 5, from a more toxic form to a more benign form. And the purpose of this work, which was very, very conclusive, is to show that the oxidation is inhibited by either filtering the water, which removes microorganisms, or by using antibiotics. And so it's a very, very clear example of the chemistry of a water supply being determined by the microbiology of the source environment. Not just by geochemistry alone, but by geomicrobiology, in fact. And the half-life of this conversion process is only about 1/3 of an hour. Second example I'd like to give is from work by our student Henrik Eilers and Norman Brooks and myself, finished in 1995. It is difficult to study the interaction between the sediments and the rivers of all the waters we would like to study. Caltech has an inclination to make a reasonable physical model of the system and to try to capture the important details. So this is a bed of sand, a long bed of sand, underlying water flowing over it in turbulent motion. This is just a schematic. The water continuously recirculates, and these are dye studies which shows the penetration of water containing dye into the underlying water. So it looks like dunes are being formed, and as the dunes are being formed, metals are going into the water, like, for example, zinc, copper, magnesium, and so forth. This is one of the important examples of a strategic approach to water quality management, which relies on laboratory work to project behavior at a large scale. And the laboratory work faces this challenge. How can we put together the fluid mechanics and the physics and, say, the chemistry and the microbiology? What you would like to be able to do is study the chemistry and the microbiological work at the microscopic and molecular scale, and you would like to understand the fluid mechanics at the level of turbulent theory and turbulent experiment. So down here I show the result from Henrik's observation. These are the large-scale observations of material going into the sand from the overlying water. In this case, it was zinc. And this is a beaker experiment made with the sand. And this shows the laboratory data on the beaker experiment. And then that is put together with the fluid mechanics to predict the observation in the bed. And this is the result. The material, zinc, penetrates further and further down into the bed and higher concentrations over time, for over 1/2 to 50 hours. The line is the predicted absorption from the beaker experiment. These are the experimental points in the sand bed, and this shows in non-dimensional time, which is a favorite of fluid mechanicians, for reasons not quite fully absorbed by me. This shows copper, zinc, magnesium, and lithium penetrating in, and the models and measurements agree very well. Now, does that mean that you could use it without any further modification? No, but this model provides a very useful guide about the next level of experimentation, which is the field level, the stream, for example, and this is applicable to sandy stream bottoms. Lastly, I return to this idea of the importance of the basal water components for the case of arsenic removal. In this particular case, arsenic removal by coagulation using ferric chloride. This is the removal of arsenic 5 or arsenate, and the experiments are, first of all, one in a simple sodium nitrate solution, which gets very large removal. The second is to amend that by adding 2 milligrams per liter of organic carbon. Notice the dramatic adverse effect on the removal of the arsenic 5. And then this is the addition of 120 milligrams per liter of calcium, which offsets and overcomes the effect of the organic carbon, dissolved organic carbon. What I mean to convey by this is that we do not understand water quality simply from a list of maximum contaminant levels. We will only understand water quality by understanding the interaction of the minor components, the nasty ones, with the chemistry that changes from watershed to watershed, changing the organic carbon, the sulfate, the hardness, and so forth. And the second example is for the removal of arsenic 3. Here, again, the nitrate solution, 70% removal. You add sulfate, it interferes, or you add organic carbon, it interferes, and then you carry out the same experiment in California aqueduct water, and whatever the ingredients are, they have some of the characteristics of the simple experiment that shows they are interfering with the arsenic removal. That means that in order to predict behavior or to rationalize observations, you must not only know the minor constituents, you must know the major constituents and rationalize the behavior. But that's what water engineers are, of course, expected to do. Okay. The last line of matrices: drinking, ecosystem, bathing, toxic chemical, pathogen, carcinogen, nutrient, source control treatment as an intervention to remove toxic chemicals from drinking water, watershed protection, disinfection and filtration as a method to remove pathogens from drinking water, advanced treatment as a method of reusing, for example, oxidation, activated carbon, ultraviolet radiation to remove carcinogens from drinking water. And then for bathing, the world of Norman Brooks and the world of other hydraulic engineers of renown, either outfalls to carry material far from the bathing area, or secondary treatment, which has been a hotly contested issue for the last 20 years for coastal discharges. And then for the case of nutrients affecting an ecosystem, for example, nitrogen and phosphorus, one of the management techniques is land management or waste treatment. Okay, so now the big four, the final four, so to speak. I want to show you what I think is the way that a useful way to organize thinking about water quality issues and water management. One, the matrix of water withdrawals and water uses. That is, the quantity taken out and the use. That leads to a water quality requirement matrix. It's the first example I discussed in my talk. The matrix of chemical components and chemical species. If you know what goes into the water, how do you predict what the form will be in the water? Well, use an equilibrium chemical model. It is very powerful and very, very instructive. Almost every problem requires this, and we might as well take it as part of our habitual approach to water quality management in the engineering and research area. And then chemical species in relation to chemical reaction rate. The most difficult problem we face, I think, because it is not amenable to a standard analysis in any way. But what we get out of this, if we have reaction rates and chemical species studied in laboratory studies or field studies, we get lifetimes in the water. How long does a compound last? Does it last 2 minutes? Does it last several hours? Does it last weeks? Does it last years? And then the water use, water quality, environmental engineering action matrix. If you know the water use, if you know the water quality, what is the series of actions available to you and what needs to be done in order to support it? And then a quick take on that. Quality analysis and quality standards are very important. Beneficial uses range widely. This is the language of California, by the way. I'm not so sure that it's universal language, but it makes sense to me, and it's not inherently anthropocentric, because we can consider the beneficial uses for the environment as well as for the humans. And water quality protection and management. And so this is the alternative, again, the Catskill example: manage the watershed, intervene with treatment. I conclude with a list of no particular argument from me, but I want to throw it out as things that you might want to ask questions about, or even better, tell me the answers to. And so I've arranged it as, what are some of the water challenges and initiatives that in the area of water quality vis-a-vis water quantity at the turn of the century? One, in some cases, will be to secure fresh waters, that is, to get additional fresh waters. The Chinese are clearly contemplating that in the transfer from the south of China to the north of China. Purify waters, use treatment, use filtration, develop new processes, protect human health, and preserve aquatic ecosystems. That's what we do in the management of the southward flow from the Bay Delta by controlling the take so that the estuary can be properly flushed and the freshwater balance maintained. Peter Glick is a strong advocate to assure a right to water for all people. He places that right at, he estimates at 50 liters per person per day. The recent world meeting in Kyoto on water backed away from endorsing this kind of a measure. The piece on it in the New York Times was extremely critical. The piece on it in some of the other journals, not critical of the lack of science, but what we will call the lack of resolve and the lack of political toughness. Because that's the world trying to compromise on an issue. Allocate water for beneficial uses, well, that's what we do in California. That's how we make decisions. And we use models to make those decisions, and we use measurements to make those decisions. Takasano and other advocates and many pieces of progress conserve and reuse water, and the issue there will always be, what don't we know that we need to know, and how can society learn what we need to know in order to make decisions about conserving and reusing water. The global issue, which is argued by many policymakers, is we must learn to use water sustainably. That is, so that this generation, the next generation, and the generation after that can have access to quantity and quality of water needed. This should have a question mark afterwards, because I imply it to be a question. What about the desalting option? The desalting option is always on the table. It's always being brought up and gradually implemented in an increasing number of situations. And lastly, also a very hotly disputed area among policy analysts for water is the pricing and marketing of water. Should there be privatization, and how should the pricing be done, and should water be a commodity in international trade, the part of the globalization debate? So I leave those as questions or assertions, you choose, and of course you probably have your own questions, and I thank you very much.
I think some people may have to get up and go if you're running late, but I also think there's time for some questions and answers. So maybe we could start. Mike, do you want to start?
Jim, there are those that argue that the approach to use of standards for drinking water criteria is doomed to failure in the long term, because there will always be more and more contaminants of interest, and we'll never be able to regulate all of them. We're only regulating 5 every 25 years. And I've argued for a treatment standard as opposed to water quality standard. Do you got any thoughts about that as a strategy?
Well, I think those are conceptually well-defined alternatives, and I think that a treatment standard has been part of the American and European tradition well back into the previous century. You say, as a society, you say how a water or how a wastewater must be treated in order to reduce the risk to water consumers to the best of your knowledge at the time. What's changed throughout the 20th century going into the new century is that the concept of risk analysis has become more and more advanced, more and more put forward as an absolutely essential rational step. And the difficulty with risk analysis is how much information can you do without in order to make a defensible and useful risk analysis. I have no inherent objection to a technological approach to the setting of standards. I also think that science, and in this I agree with a position taken by the late Werner Sturm some 20 years ago, which is exactly that the normal human impulse, especially in the United States and Europe, which is to measure everything before you know the truth, is doomed to failure because it doesn't rely on scientific principles. That is, it doesn't rely on reasoning based on what you already know and analogical reasoning to make intelligent guesses. Now, in our society, I think we're a very pragmatic society by and large. And I think there's a show-me attitude that says, well, if you can't measure it, how do we know it's dangerous? That's not resolvable by science. There are certain issues, in my view, that are not resolvable by science. They depend ultimately on more complex things like human values and the value of water and human values. I gave a talk at UC Santa Cruz 35 years ago on the contamination of coastal waters. And I talked about the science that I was doing. And Henry Kendall, who was later to form the Union of Concerned Scientists and also to receive the Nobel Prize in Physics about 10 years later, rose up and said, "You've talked only about the science. What about the religious and ethical belief of the people who are affected by this?" And I was absolutely unprepared for such a question, but I've never forgotten it. What it tells me is that we do not live by the science alone. We have to do the best science we can, the science that the society can afford, and then we have to consciously say what the risk is that we're taking and make a policy decision. So technological standards are a very clear alternative, but even then you face a certain amount of the unknown. One of the students asked me today in a class, how do you base policy and standards and how do you develop things when the concentrations are 10 to the minus 12 moles per liter? My answer to that is that's not inherently a daunting scientific problem, but the question is, does the society want to go that way and measure compound after compound after compound? The other way to do it is what Sheldon Friedlander, my Caltech colleague now at UCLA, called technological forecasting. Use your reason. Look at what industry is doing. Look at what agriculture is doing. And then identify the high priority items that need to be measured before anything else is measured. And then satisfy yourself that you have those under control, and then make a societal decision. But it's a very interesting thing in America that in a way we're very unhappy when science doesn't tell us the answer. But in another way, we're unhappy when science does tell us the answer. Because that's inherent, I think, in the dubiousness of human people about scientific authority. After all, we've been misled very often. Not necessarily deliberately, but certainly misled.
Okay. One of the things I noticed that was absent in your matrices is the cost component. And why I'm curious about this is because most of our policymakers are not scientists. They're politicians and lawyers. You know, this is a diverse crowd, so I'll throw in no offense. But I just wonder how much, in your experience, do policymakers really respond to what we find in science? Because I heard a slogan that says, the average man is not an environmentalist until his child develops some strange cancer.
Even the United States congressmen and senators are not environmentalists until their child develops or their grandchild develops some strange disease. Mm-hmm. So what was your question?
Well, my question is that where does, can you factor money into this? I mean, we've known about Cryptosporidium hurting the immunocompromised, I think, since for about 20 years.
Right.
And how many towns have really gone into filtration to get rid of Cryptosporidium. So how much of this is money-driven and not science-driven, do you think?
My best advice for you is to read Ibsen's A Public Enemy. And if you read A Public Enemy, you'll find out that the community does not want the doctor to tell about the communicable disease that's been found in the water baths, which are a major tourist attraction to the town. And the reason is that they will lose the income which they've come to be comfortable with. You will never avoid that tension within the human society. Some leaders are more able to change public perception and public motivation. We've lived in some times where some presidents and some congressmen like Stuart Udall were able to motivate people to do things that they might not have wanted to do and to spend the money on things that they might not have wanted to spend it on. But there's always going to be that trade-off. And I think what science can do to the best of its ability is show the options. I deliberately never use dollar signs in any of my remarks because dollar signs are nothing but stand-ins for value. We value water in relation to other things. It's reasonably, although I made the joke of showing how much I paid for water, that's meaningless. It's really in relationship to other things that I spend money for. I have to value things in relation to one another. So I don't think it's cynical to think that money weighs largely. I think money weighs largely in everything we do, and at this particular time in American history, I think that money is probably in the saddle. If you want to have one person's view of that, read the book, The Best Democracy Money Can Buy, which is recently reissued. It's about money, and I think our job is not to get into that, but to, as scientists and engineers, is to show clearly what the alternatives are and to show what in present dollars they cost, but we will in general not determine those outputs. That's why policy is up in that box on the right-hand side. The dollar decisions are made in costing the process by the engineers, and the risks are made by the people who set the criteria at some level or some standard. But the policy is what the Congress and the state legislatures and the executives do. That's why we elect people to help us to carry out those decisions. I don't have any other solution to it. Just be as smart as you can and tell as much as you can to the policymakers. Make them smart.
In these matrices, another interesting axis is public and private. In terms of public values and private values, there is this thing with water called public trust. Yes. And scientifically, the notion of the precautionary principle in terms of perhaps how to apply science. What do you think about that?
By another name, I think it's called prudence. Yeah. And I'm very, very much in favor of prudence. But who among you will speak against prudence? No, the serious answer is that requires the sort of thoughtful judgment and reflection that I don't normally bring to the table because my specialty has been saying what's possible in the world of science. But I tried to imply and not develop because of my limited abilities in my left hand versus right hand. In my original slide, I had a middle row which had the hands clasped together. And it showed some of the things that are not resolvable either by the right hand or the left hand, and are in the area of human values, private and public. For example, I would be very concerned if privatization meant that the privatization led not only to the management of the waterworks, but the setting of the standards for the waterworks. See, I don't think that the best interests of the citizenry is looked after by any corporation, because I don't believe corporations are moral or immoral. I think corporations are interested in objectives, in meeting their needs. Those are. But if we privatize water and the government continues to play the essential role on behalf of us as citizens of formulating criteria, investing, because the development of criteria is very costly. That's one of the other places where the dollar sign comes in. It's not just even to get the information that will go up and inform the policymakers is a very, very costly enterprise. And that's maybe another reason why Michael Kavanaugh's not personally pessimistic, but articulation of a pessimist is reasonable. It costs a lot to do the science that's necessary to just inform us about what the alternatives are. And at some point, some societies will not pay that because there are other things they must pay for. So I don't think that's a satisfactory answer because I don't have a satisfactory answer. I recognize that public and private values are an inherent conflict, and I have to tell you that in politics, I come from the left. That's all I can tell you about that. And I agree with Noam Chomsky that corporations and governments aren't moved by morality, they're moved by results. And our job as citizens is to hold the government to the consequences of the results of their actions.
Jim, I want to take the host's prerogative to ask the last question. I think all of the questions here have dealt with, in one way or another, public perception. And in your water quality matrix, you talked about the role of science and technology in policymaking, but I never saw education or the role of an educator informing public perception and the values. And I'm curious how you reflect on how well we're doing about transmitting this knowledge about science and technology into the decision-making process, especially in California.
It's a good point, and I feel very caught out as a person who spent 45 years teaching in universities to not have put the word education on my slide. I can only say in defense that it's always been implicit in my activity, but I have a couple of comments about that. One is that there are two forms, at least, of education that high schools and universities are urged to deal in with respect to a public issue such as the environment. One, following the example of William Bennett, with whom I do not agree, is that the universities and the high schools should be engaged in moral education, and that we should be inculcating values that will then cause the citizenry to behave in the right way. The other important part of education is through science and natural science, molecular science, all sorts of science, to understand how the world really works. If you don't understand how the world really works, then you're at the mercy of people who will tell you what your values ought to be and the way they think the world really works. There's a famous quotation due to Francis Bacon that said, "In order to command nature, obey it," which means that you must understand the world in which you live in order to take sensible action on your own behalf. So I think in education, I think there's a kind of moral education going on in the United States which I don't admire, which is to frighten people either from the right or from the radical left, which is to talk about slogans and to talk about pollution as if it were a fully understood process. And I mean, we almost are talking about good versus evil in some of the dialogues that go on, and my own preference is not to see it that way. My own preference is to see what's actually going on in the groundwater, what's actually going on in the surface water, what are the real options. So I think the education, we have invested so much in the last 30 years in environmental education compared to what we did in the previous 70 years that I would say we're doing an extraordinarily good job. And not all universities are like Caltech. Thank goodness for all universities, because we don't spend a lot of time at the graduate level. And we don't spend only 20% of our time at the undergraduate level in teaching about history, philosophy, ethics. When I read Peter Glick's statement in one of his previous articles that every human being on the planet has the right to the water necessary for life and placed it at 50 liters per person per day, I immediately called up our ranking Caltech scientific ethicist, David Goodstein, who's also the vice provost. And I said, "David, I've just read that every human being on the planet is entitled to 50 liters per person per day." I said, "What do you think of that?" He said, "What sort of a question is that? He said, in California, we put bricks in the toilet and we pay outrageous prices. What are you asking me this question for? And I said, I think it's a moral question. He said, of course it's a moral question. It's an ethical question. We don't deal in that. That is, in our science. Other people deal in that. And the reason I called David is that he teaches a course in ethics and science together with a professor of philosophy. But he was very, very clear. That's not a statement that I can comment about as a scientist, but I can comment about it as a person who values human life and who values... And in that area, I think that we're deficient in education. Not to brainwash people, but to really teach ethics and not to teach how to behave, but to teach the method of analysis of ethical behavior on environmental problems, medical problems, and a whole host of problems.
With that, those are apt words to end with. Thank you very much, Mr. Northern.